yours. Thank you.
Thank you. And thank you, Micah. Hello, Qiskit advocates. It's nice to be here. I'm joining you from Waterloo, Canada. Today, I'd like to tell you about Samplomatic and the Executor, which are tools for circuit randomization and a new execution model to help with modular error mitigation. A bit of history. So when we first introduced the runtime primitives many years ago, we had this idea of a resilience knob, with the idea being that the bigger you sent the integer in as, the more mitigation we would attempt on your inputs. Coinciding with the release of primitives v2 in 2024, we extended the idea of the resilience knob to guided control, where you could tweak the settings in a more fine-grained way and override resilience settings in many ways. And today, what I'm talking about is a third phase of this evolution in mitigation via the runtime primitives, which we are calling modular error mitigation, where you get near complete control of your mitigation workflows on the client side. It introduces more transparency to our services. And these are the new tools in phase 3. And I'm breaking them into 3 pieces. So there's Samplomatic. This is a Python library for circuit randomization. I'll talk more about that. It's vendor agnostic, like the Qiskit SDK. It has tools to implement error mitigation protocols. And it very uniquely describes the process of randomizing a circuit as a graph object, which that library calls a samplex. Then there is the executor. This is a new low-level primitive alongside the sampler and the estimator. You will see it as sampler-esque. It also accepts samplex graphs as a native input to the job. And finally, though I won't talk about it much in this presentation, there is a refresh of the noise learner, um, which works well with the 2 tools, Samplomatic and the executor. So why do we want to randomize circuits? I should probably start there, and I'll describe how we randomize them, but first, why? So I'll break it into 2 categories. Maybe there could be more, but roughly there's twirling and there's mitigation. So twirling is the process of taking one circuit of interest and instantiating many random copies of it in a very structured way, with the goal of removing coherent parts of the noise. So if you look at any quantum noise channel, you can basically do a polar decomposition on it, and you can describe the noise as consisting of a stochastic probabilistic part and a coherent unitary part, which is like a rotation. And twirling, at least polytwirling, removes the coherent parts of the noise, and what you end up with is a more predictable stochastic noise process. Um, Coherent noise in general, especially adversarially, can build up faster than stochastic noise, so that's not so nice. But probably most importantly, twirl noise models are easier to learn with learning protocols, and they're easier to reason about. Both of these things are crucial in many randomized based mitigation methods. Mitigation, in randomized based mitigation, randomized noise injection is a very powerful tool to mitigate quantum noise. So just to pick 2 examples, you have probabilistic error amplification, where you amplify the noise in a quantum circuit by known amounts, and this lets you extrapolate back to the 0 noise level. Or probabilistic error cancellation, you can inject anti-noise channels. It comes with a high classical overhead, but you can effectively remove noise processes from your circuit under fairly general assumptions. And just to pick 2 random papers from literature, right? So the top one is out of the Berkeley group. This paper is a few years old, and what they did is they constructed a quantum Fourier transform on 4 circuits, and they fed it some input states. So you can see this top plot here. They're feeding the QFT the 0000 state, and then they're performing it with and without polytwirling or randomized compilation. And ideally, if you do this, you should end up with an equal superposition over all of your output states. And so ideally, you have these outlined black squares. And if you do randomized compiling, you can see that your actual observed results are very uniform. But if you don't do randomized compiling, your coherent errors can build up in strange ways, and you see that some boxes are very much overestimates and some are underestimates. And so polytwirling is buying you predictability. And in the second example down at the bottom, this is an IBM paper where they were looking at some trotterized chemistry application. um, you can see that as you increase the number of randomizations, you slowly get a better and better output in this particular application, right? And this is how we randomize, or this is at least how we polytwirl. So if you take a CNOT gate, because it's a Clifford gate, you can choose a random set of polys to put on the left of your CNOT gate, and then you can put a correction to the right of the CNOT. So even though you've inserted some random polys into your circuit, it still implements a CNOT. Now, you do this all over your circuit for all your CNOTs, and you make a bunch of random circuit instances, and you execute them and all of your circuits are logically equivalent. Um, and you take all your data, and you average it together, and you pretend that it came from your base circuit. That's the premise. But is this a good strategy on IBM quantum hardware? Well, in the last couple of years, as you can see with the dramatic increase in our CLOPS, our cycle layer operations per second, we've become highly optimized at compiling at the low level parametric circuits and executing them really, really fast with different parameter values attached to the same compiled payload. And we can potentially execute millions of randomizations per hour under this scheme. So whenever you're talking about, and this is a general rule for IBM quantum hardware, whenever you're talking about getting through lots and lots of circuits, if you can structure it as a template parametric circuit and a big array of numerical values to plug into it representing your different instances of that circuit, we can execute that really fast. So when you think about the twirling strategy, what you don't want to do is actually make a bunch of quantum circuit instances and send those all into, for example, the sampler. What you instead want to do is um, write down your circuit parametrically. In this case, we have 12 parameters, which are the RZ angles. And you want to describe your randomizations as numerical values that you plug into these 12 slots inside of your template circuit. And this is what Samplomatic is going to be good at. So Samplomatic is available in PyPy. You can pip install it today. And this link is what I shared earlier in the chat. So let's do a hello world. Okay, this is how you might think about instantiating a circuit, right? So we're just adding a Hadamard and some C naughts and some RX gates, which depend on a parameter called theta, and we're measuring all the qubits. Pretty simple. This is what Samplomatic wants you to do. It wants you to use this new instruction that was added in Qiskit 2.1, I believe, called a box instruction. A box instruction is just a scope that you can put inside of a quantum circuit, and you can throw any other instructions you want into the box. You can also annotate boxes. So what you can see here is that from Samplomatic, I'm importing an annotation called twirl, and I'm declaring inside of my circuit that I would like the Samplomatic interpreter engine to twirl these boxes with polys, right? So I haven't actually done the twirling yet. I've just declared my intent that I want to twirl them. And you can see what this looks like after I've drawn the boxes that I've put into my circuit. And then what you can do is you can import a function called build from Samplomatic, and you can run it on your boxed up circuit. And this build function will return two values. It will return a template circuit, and it will return a samplex graph. The template circuit is what you will be submitting to hardware, to the backend, to be executed. It is just a regular parametric quantum circuit. The samplex object is an object that describes the process of randomizing my circuit. It doesn't actually contain all of the numbers that perform randomization. It stores the process of randomization. And we can query it. So our original circuit had one parameter called theta. And so to the samplex.sample function or method, I need to tell it what value to assign theta, and I can tell it that I want 5 randomizations, and then I can call the sample method, and the samplex will perform randomization and give me a bunch of numbers, or actually a dictionary of arrays. And so for example, since my template circuit had 21 parameters, oh, this is a typo, I should have a 5 by 21 float array of numbers, which implement twirling of my base circuit. And you can do neat stuff, right? So everything I just described is available client side. There's no twirling server side happening here, right? So for example, if I take my base circuit, this is just a bunch of code that will plot the unitary implementation of my circuit as a figure, right? So this is what my circuit looks like in this example. And I can go through each of my 6 randomizations and I can check locally that indeed randomizing my circuit doesn't actually change the logical nature of my circuit. Every time I plot its value, it looks the same. So sampling is working as expected in my samplex, right? So I can gain local trust and transparency that my circuit is being twirled in exactly the way that I specified with Samplomatic. Um, in the first example, I drew my boxes manually inside my circuit. So I said with circuit.box to create box instructions. I should also point out that Samplomatic implements a boxing pass manager. So if you don't want to box up your circuits by yourself, you can use this function to generate a pass manager that will box up a circuit for you. So you can see if you instantiate your circuit as on the left, this boxing pass manager under these settings will draw boxes as depicted. Now, Samplomatic does not help you execute. It is vendor agnostic. It just helps you with defining randomization um, and implementing randomization, but it doesn't actually submit anything to hardware for you. That is what the executor primitive is for. So what Executor does that's fundamentally different than the sampler is that it accepts the samplex sampling graph as a native input, right? So if you need to do a million randomizations of your circuit, you don't send in a big array of numbers that has a dimension equal to a million somewhere. Instead, you send in your circuit, you send in your samplex graph, and it will query the samplex graph for you server side inside of the runtime environment. And so you can see here, syntactically, what we do is we construct something called a quantum program. We tell it every configuration needs 64 shots. We append a couple of circuits to it. So first, we're going to append a template samplex pair. And then we're going to append a circuit with no samplex, right? Because the samplex is totally optional to the executor. So in that sense, it's nearly a drop-in replacement to the sampler. Um, and the way you should think about an executor is it's an array in, array out mechanism, right? So you send it your circuits and your samplex. So you also send it array inputs to your circuits and samplexes if they happen to be parametric. It's going to do all of your processing with the QPU server side. It's going to collect all your results into a bunch of arrays, and it's going to give you these arrays back. And so when we look at the job outputs of the executor, you can see that they're formatted as results. And so we get back all of our Boolean bit strings as big arrays. But also if the samplex returns other information other than parameter values that we require during mitigation post-processing, the executor will also return those values to us. You can see here that it's returning us some information about how it chose to randomly flip our measurements. In this talk, I've sort of gone very quickly through some very simple examples involving polytwirling. I want to point out that Samplomatic is actually quite a bit more sophisticated than this. It doesn't just do polytwirling. It does things like let you specify basis changes. It lets you inject noise from learned noise models that you might learn with the noise learner. In this demo that you can also see at the link that I set, there's a very thorough demo of implementing probabilistic error correction with a technique called shaded light cones, right? So you can see here that inside of our boxing path manager, we're not only telling it to twirl, we're also telling it that we want the ability to inject probabilistic noise into our circuit at execution time. And we can send in these so-called light cone opacity filters to it, and this will help with this PUC shaded light coning technique. Um, so let's talk a little bit about the future, give you some hints of where we're trying to go with this throughout the year. So first of all, we'll continue adding features to Samplomatic. We'll add new twirling groups. We'll do this, we'll do that. The estimator and sampler abstractions will not go away. Those continue to be useful abstractions. However, since the executor is a lower level primitive than both of them, one could think about implementing the estimator and sampler abstraction using the executor as a backend. And that's something we're thinking about doing. And what this would buy you is it would give you a totally open source implementation of error mitigation. So you could look under the hood and see what's going inside of your estimator. You can also think about the samplex object as an optional semantic to the quantum program, right? So you saw in the example that you didn't need all quantum program items to have a samplex object. It's optional. And you can consider other optional semantics inside of a quantum program. And so the one that we'll be thinking about most immediately is adding semantics for computing expectation values to the executor, which will help, obviously, if you were to implement an estimator via the executor, you could do that with these kinds of semantics. All right, that's what I've prepared. Thank you, everyone, for your attention.
Thank you so much, Ian, for that presentation. I am now going to pull up me and Micah. And feel free to drop your questions in the chat, everyone. We do have a couple of questions already.